has started.
Alright, so let's review the equations. As I just said, this is already posted, and we are going to attach this to your exam papers as well. So here we have some physical constants. Those are the constant numbers, like the electron charge. Q equals to 1.6 times 10 to the negative 19 Coulomb. And the vacuum permittivity, epsilon 0, is this number. And then intrinsic carrier density of silicon, Ni, equals to 10 to the power 10. So this is at the room temperature. So what is the room temperature? Room temperature is like 300 Kelvin. And then if you convert that into the thermal voltage, then it will be Kb T over Q, and Kb is the Boltzmann constant. T is your 300 Kelvin. And then if you divide by the Q, which is this Q, then you get 26 millivolts. So what is milli? So here is the scale we use. And then milli is 10 to the negative 3. And then the dielectric constant of silicon and silicon dioxide. So what's this? So this is the relative permittivity. So if you have a plate capacitor, you have the total capacitance C, and then it depends on the distance here, the oxide thickness, let's say TOX. Then the COX, for example, if this is MOS cap, MOS, then the COX is the capacitance per unit area. That is normalized to the area. If you think about the area of this one is A, then the total capacitance divided by A is the unit area capacitance, and that is COX. COX is epsilon divided by the thickness of the oxide. And this epsilon is from, let's say, the epsilon 0 multiplied by the relative dielectric constant for the oxide. So epsilon 0 is for the vacuum, and all the materials are normalized to the vacuum permittivity by this relative constant. So for silicon dioxide, it's 4 here. So it's 4 times of the permittivity in the vacuum. So you need to use that to calculate the COX for the MOS cap. And then in this class, we assume the Nc equals to Nv equals to 10 to the power 19 per centimeter cube. So this is the effective density of states in the conduction band and valence band. So use that to calculate the electron density or the hole density. And for the silicon, the band gap Eg is 1.1 electron volts. So any questions here? You will refer to those numbers if you need to calculate something in the exam. Will the temperature in this class always be a constant 300 K? So for the numerical calculations, yes, we will assume 300 K. But in conceptual questions, we may ask you if the temperature increase, then what will change? Let's say qualitatively. But quantitatively, if you want to calculate something, we are always going to use 300 K to calculate the numbers. Okay, and then the equations for the conductivity of the metal, like the sigma equals NQ mu. N is the electron density in the metal, Q is its charge, and mu is the mobility. So we may give you the mobility of the metal if needed. And the resistivity of metal is, rho is 1 over sigma. Intrinsic carrier density in the semiconductor like silicon, Ni, is given by this formula, depends on the Nc, Nv, and the band gap, and of course temperature. And as we discussed, at room temperature for silicon, is this 10 to the power 10 per centimeter cube. And then electron density, we use the Fermi statistics. Then we have this equation for the electron density, and n equals to nc, and the exponential, the relative distance between the Fermi level and the conduction band edge EC. And similarly for the hole, then it's related to the EV, the valence band edge. And then for the p-type semiconductor, we have doping, the acceptor density Na, and then one acceptor contribute one hole, so the hole density P equals to Na for the p-type. And then for the N density, the electron density, then you can always use NP product, because NP always equals to Ni square. So if you know the P, then you can get N through this Ni square. And similarly for the N-type semiconductor, the electron density will be the same as the donor density, because one donor gives you one electron. And then you can get the hole density by the Ni square. Any questions? So for resistance of the resistor, this is like Ohm's law. And resistance equals to resistivity times the length divided by the area, the cross-sectional area. And then Fermi function. So this tells you the probability to find the electron at certain energy level E. And then here, this one, if the energy is the same as the Fermi level, then this function becomes 1/2. So at the Fermi level, the probability is always 50%, because the Fermi level is a reference level. And then Boltzmann approximation. So if the energy is much higher than the EF, for example, in the conduction band, then you can approximate this Fermi function as this exponential decay function. So this is because if you think about the EC, EV, and then your Fermi function is somewhere here. So this is the energy level E, and this is like your Fe. So this probability is like exponential decay function to the conduction band. Or in the p-n junction, we showed the electron distribution. It's like you have more electrons here, less electrons here, and much less electrons here. So this is like a exponential decay function here. The higher the energy, exponentially less electrons available. So this is the Fermi function. And then the drift velocity, okay, for electron, we have the velocity equals to mu E. Mu is mobility. Here, elective sign is for the electron. And for the hole, you will have the V equals to mu E for hole. And then for the drift and diffusion, then the electron and hole will have the equations like this. Then the first term is drift, second term is the diffusion. And for drift, it's proportional to the electric field E. And then the diffusion is proportional to the gradient of the density, like dN over dx. And then we can use the net current equals to 0 to derive the Einstein relationship. And here you have this D equals to KT over Q times mu. Any questions? And for the p-n junction, so the current versus voltage, the IV relationship is given by this equation. And if you draw it, then you have I and V. So this equation is something like this. So at 0 voltage, 0 current. In the forward bias, then this is exponential. In the negative bias or reverse bias, then the current will be saturated to the negative I0. And then the built-in potential, that is for the PN junction, we have this barrier. This barrier height is given by this formula, and it depends on the doping. If you have higher Na or Nd, then the barrier height will increase. And then the MOS cap. So first, the gate voltage you apply dropped on two components. The first one is the oxide, second one is the silicon surface potential. And then for the oxide capacitance, as we just mentioned, COX is epsilon 0, that is the permittivity for the vacuum, times the relative dielectric constant, epsilon OX, then divided by the thickness of the oxide, TOX. And then the depletion width is given by this square root respect to the phi s surface potential. And at the threshold condition, we just discussed phi s equals to 2 phi b. Then you plug in the 2 phi b, then you get the maximum depletion width. Because above the threshold, then the phi s is almost fixed to be 2 phi b. That means the depletion width W is almost fixed to the W max. So this is the maximum. And then the threshold voltage is given by this equation. And actually, it's like a gate voltage is dropped on the VOX plus the phi s. And at the threshold, this phi s equals to 2 phi b. And then the VOX is given by this square root. So phi b is the difference between the Fermi level and the intrinsic Fermi level. And if you want to calculate that, it's you can use the Ni for that, because Ni is respect to the Ei, the intrinsic Fermi level and the intrinsic carrier density. So it's KT over Q natural log N A over Ni. So that is a phi b, and then you get 2 phi b. So the threshold voltage, if you look at this equation, actually as a designer, you can only change the doping and the thickness of the capacitor. You cannot change other parameters because others are physical constants. So that means what? Like a MOS cap, if you want to change the threshold, what you can do as a device engineer, then you can only change the thickness of the oxide and then the doping to the substrate. This semiconductor, we have the Na. You can only change those two numbers because the TOX will affect the COX, and then the rest parameter here, you see epsilon and Q, those are the physical constant. And then you can only change Na, and then phi b actually depends on the Na. You see here phi b depends on this Na. So once you change Na, the doping density, then you change phi b, so you change the threshold voltage. The others are physical constants. Of course, depends on the temperature. So you have Kt and Ni, those depends on the temperature. But if we fix the temperature to be 300 K, then you cannot change the threshold unless you change the Na or the TOX. All right, any question? I think that's all for the materials in the first midterm. And although you have 24 hours time window, I would expect that you can finish this within like 2 hours, given the number of questions we have there. And what else? So if you have any question during the during the exam, please post your question using the, let's say, the Piazza discussions here. So either me or the TA can clarify your question. So let's use this so everybody can see the clarifications. Okay, so any other questions regarding the first midterm? Will be any extra credit on the exam? No. So the total available points are 100. So that is what we have on the exam. We don't have extra question or extra bonus. Okay, any other questions? If not, then we're going to stop today. And good luck for your homework, midterm 1.